Welcome back everyone. In this lecture I am going to tell you algorithmically how to recover a given root system from its Cartan matrix. So, in the last lecture we actually proved that Cartan matrices determines root systems uniquely up to isomorphism. So, we will also see algorithmically how one can actually recover the root systems. So, let us fix some notations and then we will actually continue. So, you take phi to be a root system inside the Euclidean space capital E. So, we say that let us say only the Cartan matrices. So, Cartan integers are known to us. So, Cartan matrix by definition. So, this is the Cartan matrix of phi. So, the thing is when we say Cartan matrix, it is already assumed that it is coming from some root system phi. Okay. It is a positive definite matrix defined to be the Cartan integers alpha I, alpha j, and this is L by L matrix where ij varies over L. So, let us say we know all these Cartan integers. So, and then we want to reconstruct entire root system. First of all, recall some facts that we have already proved. So, recall that. So, again pi is already given, because once the Cartan matrix is given, then pi is also given, which is we label it as alpha 1 etcetera alpha L. So, what we have proved, so given beta from phi plus, so we can write beta as some beta 1 plus etcetera plus beta t, where each beta I comes from pi, such that, so this partial sum beta I plus etcetera plus beta t, it is always the positive root. So, you can write always beta as sum of these positive roots, and then if you break at any point, then it is again positive root, sum of remaining terms again positive root. And note that the inner product between beta alpha is always non-negative for all alpha beta inside pi and alpha not equal to beta. So, in this also immediately implies, or as a consequence we can see that because pi form a base. So, we also proved that beta minus alpha is not a root for all alpha beta inside pi, such that alpha not equal to beta. So, these are all things we have already proved. So, we also observed something about this alpha string through beta. If we take alpha string through beta, so for alpha beta now any roots, so the alpha string through beta, so that is defined to be S of beta comma alpha. So, which is you start with beta and then see how much you can add a multiple of alpha, and then how much you can subtract multiple of alpha. Let us say you can do up to beta minus r alpha and then beta plus q alpha. So, we proved that this entire chain lies inside phi, and q and r chosen to be max such that this interval lies inside phi. So, then there is a relationship between this r minus q and this Cartan integer beta alpha. So, the relationship given by the Cartan integer beta alpha is equal to r minus q. So, all this information that we have already proved before. So, we are going to use this in our algorithm. So, what we will do, we will recover the roots of phi using the height of the roots. Okay. So, for each height we will just recover the roots. Suppose height of alpha is 1, alpha is in phi, and then height of alpha is 1. So, it is first to note that it is enough to recover only the positive roots, because all the negative roots are just negative of positive roots. So, we first reduce to the positive roots. So, if alpha is in phi plus and height of alpha is 1, so then it is immediate that alpha must be inside pi. So, basically this is characterization of height 1 elements. So, height of alpha is 1 if and only if alpha in pi, but all the elements of pi are already known. So, pi is given to be alpha 1 etcetera alpha L. So, now what is about height 2 elements? So, to get height 2 elements we have to sum two different roots, because the only multiple of any root is plus or minus alpha. So, to get height 2 root, what we need to do, we have to take alpha I and then sum it with alpha j for some j. So, this must, so these are all the only possible height 2 roots. But you can see that since alpha I minus alpha j is never a root. So, then if you consider this alpha I string through this alpha j. So, then it will exactly start with alpha j and then you keep adding alpha I and so on up to some alpha j plus q alpha I. So, now you can see that this q must be given to be minus alpha j comma alpha I. So, this is the case. So, in particularly since we know this Cartan number alpha j alpha I, so that angled alpha j alpha I, in particularly we know this q. So, in particularly we know all this alpha I string through alpha j. So, all these strings can be recovered, in particularly height 2 elements can be recovered. So, height 2 elements of phi are recovered. So, now you can also see that in case if you are going to actually if we take height of alpha to be 2, okay, if you are interested in recurring this height 3 elements. So, then you have to start with height 2 element and then you can add some alpha I. So, that is the way to get height 3 elements. So, let us say alpha is in phi such that height of alpha is 2. So, then you can see that you can actually max you can subtract alpha i's twice from alpha for any alpha I in phi. So, let us so let us say you have alpha which has height 2. So, then take alpha I from pi. Okay. Now, look at alpha I string through this alpha. So, then you know that this has to start with alpha and then you will be adding some alpha I and so on, some alpha plus q alpha I it will end, and similarly you will be subtracting some alpha I and then it will end alpha minus alpha I. So, the very first climb this r must be at most 1. Why that is the case? Since height of alpha is 2, so you can't subtract alpha I twice. Okay. If you subtract alpha I twice, then height will go down by 2, then alpha minus 2 alpha I will become 0. So, that forces alpha will be multiple of alpha I, that is not the case. So, then r must be at most 1. So, you can see that when you can actually subtract, that again you can get it from the earlier result that we proved. If alpha I is actually positive, so then we will be able to subtract alpha I from alpha. Okay. So, in a way we have some understanding of determining this r. Okay. So, this integer r either it can be 0 or 1. Okay. So, for each root alpha of height 2, the integer r for the string alpha is string through alpha can be determined. So, that is because it can be at most 1 and we have some way of understanding when it can be 1. So, from this you can immediately determine what is Q. Q is because Q is equal to R minus this Cartan integer alpha and alpha I. Since we have determined all the height 2 elements already, so that means alpha alpha I, this Cartan integer is also determined for all alpha height 2 alpha. So, that means this is also now determined. So, once this is determined, so that means this entire alpha I string through alpha V is determined. So, that way we have determined, for example, height 3 elements. Okay. So, now using our earlier result that any positive root can be written as sum of the simple roots, you can see that with this procedure, if you go further and further and at some point, okay, some finitely many steps, you will be able to recover all possible roots of phi. Okay. So, this way we can recover all possible roots or positive roots of phi. So, this algorithm is actually somewhat very much working algorithm. For example, you can actually try to use, so for example, you can do this rank 2 case, or later maybe I will actually list all the Cartan matrices that are actually associated with the irreducible root systems. So, you can take rank 3 Cartan matrices and then use this algorithm and then determine all possible roots. So, that way you can convince this algorithm works. Okay. So, now once we have defined this Cartan matrix, it is easy to define what is called this Coxeter graph and Dynkin diagrams. Okay. So, these are all the important things that are used in order to classify this finite irreducible root system. So, what are all the Coxeter graphs and Dynkin diagrams? Okay. So, here is the definition. So, again what we do, we start with this Cartan matrix. In particularly, we take your base pi which is sitting inside phi, then pi you label it as alpha 1 etc. alpha L. So, note that given two distinct roots, okay, so if alpha beta both are let us say distinct roots and positive roots. So, then if you just compute this term, the product of this Cartan integer associated with alpha beta and then beta alpha, we have seen that. So, this must be one of these following numbers, either 0, 1, 2 or 3. Since beta alpha the inner product is positive. So, this has to be positive non-negative integer. So, this can take value from 0, 1, 2, 3. So, this is something we know already. So, now what is the Coxeter graph? Coxeter graph now easy to define using these numbers. So, you take Coxeter graph to be, so what are all the vertices? The vertices are nothing but all the simple roots. So, that is capital pi. So, there are L vertices. So, now what we do, we join ith and jth simple root by this number alpha I beta alpha I alpha j. Okay. So, what let us say what are all the edges. So, draw alpha I alpha j times alpha j alpha I number of edges between ith and jth vertex or simple root. Okay. For example, if we take B2, so then there are only two simple roots, let us call them 1 and 2. So, then you know that if alpha beta and beta alpha, so this has to be 2 there. So, the Coxeter graph corresponding to B2 will look like this. For G2 again this number alpha beta times beta alpha. So, this is going to be 3. So, for G2, so there will be 3 edges between 1 and 2. So, these are all the Coxeter graphs. Of course, the Coxeter graph determines the numbers, the Cartan integers alpha I, alpha j, in case all the roots have equal length. But we have already seen that that is not the case. For example, B2 and G2 they have different root lengths. Exactly for irreducible root system, we have seen that at most 2 root lengths can occur. So, and exactly B2 and G2 have 2 distinct root lengths. So, in this case the graph that actually fails to tell us which of a pair of vertices should correspond to a short simple root and which to a long simple root. So, in particularly Coxeter graph is not completely recovering what we wanted. Okay. For that purpose what we do, we introduce what is called this Dynkin diagram. Of course, the Dynkin diagram, the base graph will be same as Coxeter graph. So, all we do is we just put arrow between long root and short root. So, basically we can add an arrow pointing to the shorter of the 2 roots. So, let us say alpha and beta. So, these are all 2 roots and then there are some edges between them. If beta is actually a short root, you put arrow from alpha to beta. So, the point of this arrow should always point towards the short root. Okay. So, this way we get what is called Dynkin diagram. For example, the B2 Dynkin diagram will look like alpha beta 2 and then the G2 Dynkin diagram will look like this. So, because alpha 1 is actually long root in G2. Okay. So, this is what happens. So, now given the diagram, it is actually easy to recover given the Dynkin diagram, it is easy to recover the Cartan matrix and we already seen that how to recover the root system from the Cartan matrix. Okay. For example, I will leave it as exercise. So, the following diagram corresponds to the root system F4. We still have not constructed what is F4, but it is interesting exercise to actually get the informations about F4 directly from the root, from the Dynkin diagram. So, the Dynkin diagram of F4 looks like as follows. You take these 4 vertices and then you put edge between them like this and then you put an arrow from 2 to 3. Okay. So, 1, 2, 3, 4 you take. So, for example, it is clear that if we take the dual of F4, okay, so the dual will be just a flipped thing. So, then you can see that the dual of F4 will be naturally isomorphic to F4. So, this is something you can observe immediately from the Dynkin diagram. So, now what is the Cartan matrix? So, the Cartan matrix, so let us try to do it. Okay. So, for example, if we take alpha 1 alpha 2 and then alpha 2 alpha 1. So, then the product is exactly equal to 1 and note that the norm of alpha 1 is same as norm of alpha 2 because both have this only one edge between them. So, now if you try to actually recover the matrix, you can see that. So, it is a 4 by 4 matrix. So, the diagonal entries all of them should be 2 because the inner product alpha beta. So, beta alpha this Cartan number. So, this is going to be exactly equal to twice beta alpha sorry. So, when beta equal to alpha what we are going to get? So, going to get 2 alpha alpha divided by alpha alpha times 2 alpha alpha divided by alpha alpha. So, this 2 get cancelled. So, then you get 4 here. Okay. So, but yeah. So, we have actually joined only ith and jth simple root by this product. Okay. For the diagonal thing, diagonal thing we already know how to fill. So, the diagonal thing is going to be not the product, it is just the Cartan number alpha alpha, which is 2, that we know. So, the diagonal entries should be 2 for any the Cartan matrix, that is obvious. So, now since this product alpha alpha 1 alpha 2 alpha 2 alpha is 1 and the inner product alpha 1 alpha 2 is always negative or non-positive. So, in particularly the entry 1 2 and 2 2 1 must be minus 1 minus 1. And similarly, you can see that for 3 4 again this is minus 1 and minus 1 and 1 is orthogonal to 3, 1 is orthogonal to 4 because there is no edge between 1 and 3 and 1 and 4. And similarly, 1 3 is also 0 and 1 4 is also 0. Now 2 4 there is no edge between 2 and 4. So, 2 4 is 0 and 4 2 is 0 and we have to determine only these two entries and those two entries you can see that. So, that is recorded here. So, alpha 2 alpha 3 this inner product alpha 3 alpha 2 that must be equal to 2. Now, the arrow points towards 3. So, that means the norm of alpha 3 is less than or equal to norm of alpha 2. So, that means both these numbers are non-positive integers and alpha 3 has norm lesser than alpha 2, that makes that Cartan integer alpha 2 alpha 3 is exactly minus 2, that is the 2 3 entry. So, this is minus 2 and this is minus 1. So, this way we can recover the Cartan matrix directly from the Dynkin diagram. And we already seen algorithm to recover root system from this Cartan matrix. So, that way we can recover completely root system from the Dynkin diagram. So, I will just state the first of all classification theorem and then later in maybe in the next class I will prove the classification theorem. So, what is the classification theorem? So, basically what it says, if you start with irreducible root system, because we already shown that any given root system can be written as direct sum of finitely many irreducible root system. So, that allows us to only classify irreducible root systems. So, in particularly equivalently we can prove that we have to only classify the connected Dynkin diagrams. Okay. So, maybe I will leave it as exercise. This is something you check and phi is irreducible if and only if the Dynkin diagram of phi is connected. It is basically connected directed graph, that is all. Okay. So, you start with phi, which is irreducible root system of rank, let us say L. So, and its Dynkin diagram must be one of the following. Okay. So, then if this is the case, so then its Dynkin diagram has only the following specific choices, is one of the following. Of course, each has L vertices. So, what are all the possibilities? So, let us see. So, the very first type is called AL. So, AL where L is less than greater than or equal to 1. So, what is this? So, this is just this path 1 2 3 L minus 1 L. So, this is the diagram. So, then we have what is called BL. So, which is L greater than or equal to 2. So, this is starts from 1 2 etc. So, where the last thing is actually L minus 1 L and the arrow is pointed from L minus 1 to L. And there is something called CL. So, again this is I will put one arrow here, this is L minus 2. Up to this 1 to L minus 1, they are all having same length, and L minus 1 and L, they have different lengths. For CL, you assume to be L greater than or equal to 3. So, then it is exactly the dual of BL. So, you take 1, 2, etc., and then L minus 2, L minus 1. So, now you put double edge here, but now you change the arrow, you just point towards L. So, CL is exactly BL dual and C2 is exactly B2. So, there is no difference. But anyway, like we do not identify, so we are giving different label to avoid the repetition. Okay, that is why we are choosing the labels very carefully. So, now there is this DL, which is L greater than or equal to 4, and then the diagram looks as follows. So, 1 2 and then here L and L minus 1. So, this L and L minus 1, they are called spin nodes, and then you have L minus 2 here and L minus 3. So, this is the type DL, and this type A to D, they are called classical types, root systems. Okay. So, this is 4 classes of infinite families of root systems. Okay. For each L, we have this infinitely many L possible, and these AL, BL, CL, DL, they are all irreducible root system of classical types. So, now we have what is called exceptional types. So, exceptional types, there are 5 of them. So, exceptional types. So, there are 5 of them, basically E6, E7, E8. So, they are one family, and then you have F4 and G2. So, they are another family. Okay. So, what is E6? How E6 looks like? So, E6 exactly looks like follows. You take these 5 vertices here, and then you add one vertex here. So, as labeling, so we choose this particular labeling to make sure that this diagram exactly looks like this. Okay. So, there is a specific reason to choose this labeling, and it will be very clear when we actually define them, and then we will actually identify the particular base. Okay. That time it will be very clear. So, E7, again E7 looks like extension of E6. So, basically you take E6 and then add one more root to this, and here again you take this. So, this is 1 3 4 2 and then 5 6 7. So, note that the part of this, okay, this part exactly equal to E6. Okay. So, in some sense these embeddings of Dynkin diagrams, okay, we will see later what they corresponds to in terms of Lie algebras. So, we can prove that they corresponds to actually embedding of Lie algebras. Okay. So, what is E8? Again E8 is extension of E7. So, you take 7 vertices like this, 3 4 5 6 7, and then as before you add one vertex here. This is 2, this is 1 2 3 4 5 6 7 8. So, again you can see that E6 is contained in E7, E7 is contained in E8. So, now we have what is F4, we have already seen what is F4. F4, we take this 4 vertices and then you put arrow here, and then you label them 1 2 3 4. And there is this G2. So, G2 also we have seen already. So, G2 is just 2 vertices, so rank 2, and then 3 edges between them, and then you say the first vertex is actually short root, the second vertex is long root. Okay. So, we will prove tomorrow that in the next class the Dynkin diagrams of this irreducible root system, they have only the following choices. So, there are these 4 infinitely many infinite classes of classical types root system AL, BL, CL and DL, and these there are these 5 exceptional types E6, E7, E8 and F4 and G2. So, these are all the only Dynkin diagrams that are possible. And we will also see, so this is actually a theorem that for each Dynkin diagram that we have here, so we will be able to construct actually root system corresponding to that Dynkin diagram. Again, that I will do it in the next class. So, what is the second theorem? So, this is the second big theorem. Again, this is not that hard, but the first theorem is actually very hard, classifying them. So, for each Dynkin diagram, so that is listed in this A to G of type this A to G, there exists an irreducible root system having the given diagram. So, that means for each diagram here we have one irreducible root system. So, that means this list exhausts completely all the irreducible root system and it completely classifies all the irreducible root system up to isomorphism. Okay. So, this is our final results about root system. So, we will actually complete the proof of this classification in the next class, and I will also outline how to actually get all these root systems of type A to G in the next class. So, I will stop here. Yeah, thanks.